I'm going to present actually quite an old idea from late 60s, flow-based programming and my implementation of this approach in Elixir. Few words about me. Currently, I'm based in Berlin. I work for Klockner.ai company, and we are hiring good Elixir engineers. You can find me on GitHub and Medium. So I'm starting referring classics. So actually, what's the problem with our current conventional approach to creating software is that our programs are very difficult to read and understand. So we're kind of concentrated on writing code for machines, but not for people. And actually, it's kind of can be explained easily, because first we studied at university that machines are stupid and we have to instruct them properly in order to have good performance. And the second, the performance issue can be easily measured. So we can say that this code more performant than this one just by measuring the time of evaluation. But when we're talking about how to express our code to our colleagues, it's hard to measure what code is simple and what code is harder to read and understand. And actually, flow-based programming is an approach to designing programs that, for me, helps us create this approach helped us create much easier to understand software. This idea is, as I mentioned, quite old, from the late 60s, was discovered or invented by this guy, John Paul Morrison. John is still active. Currently, as I understand, he works on implementation of flow-based programming for Go programming language. You can find his articles on this page, and also there is a book about flow-based programming, and also there is a Discord channel about flow-based programming where people from different communities, from different programming language are trying to implement, to implement this idea in different programming languages. So what's the idea behind flow-based programming? The idea is actually really simple, and I think that most of you are familiar with this idea, because today lots of low-code or no-code systems are quite popular, when you just drag and drop some boxes, connect them, and magically you have a working program. So basically, flow-based programming is about that you present your program as a network of independent processes, independent components that are put in some topology, predefined topology, and you pass data through these processes, and each process transforms data in some way, and on the exit, like the result of your program is the data that appears at the end as a result of all these transformations. A couple of ideas, a couple of terminology. So these processes, these black boxes called components, and data chunks that pass through these components called in flow-based programming information packets, or just IPs. And one important thing about the flow-based programming is that all these components works in parallel. So actually, these are independent processes that can process these events in parallel. So if you push several hundreds events into a pipeline, one component works on one event, previous component works on event that comes next. So each component kind of does some work. And also, back pressure mechanism should be implemented to not overwhelm your components, because when you create a pipeline of components, it might happen that some component is slower than previous one, and it can be overwhelmed by data from the previous component. So this back pressure mechanism is also kind of basic idea of the flows-based programming. A good metaphor for this approach is assembly line, that very simple to understand for engineers. For example, on this picture, you see soft drink bottling factory. When you have a bottle, your data chunk, then first bottle goes to filler component that fill it with juice, then capper component that put caps on it, and finally label component that puts label, and that's it. The logic is done. You have a drink. There are some examples. There are some problems in software engineering that can be easily implemented with such an approach, but quite hard to implement with conventional approach, with functional object-oriented approach. As an example, the famous telegram problem, when you have a stream of lines as the input, and you have to produce a stream of another lines, but different lengths. So you have to split the lines by words and then compose lines of different lengths. And this problem actually not so easy to solve using conventional approach, but naturally solved with flow-based programming, when first component reads the sequence of lines, the second component called decomposer, it decomposes these lines into the words, then words pass to the third component called recomposer that recomposes these words into lines of another length, and finally the first component writes this sequence as an output. Okay, what is flow-based programming good for? I would say that this approach cannot be really good for domain logic, and there are several reasons for that. First of all, domain logic may be quite complex, quite algorithmic, and it's kind of hard to imagine how to traverse tree or sort list or something, how to implement this logic using this approach. And also we have kind of lots of already implemented algorithms that modifies data in place, and these algorithms are much more performant than algorithm with flow-based programming approach. Yeah, and the second point is also about performance consideration. So some tasks are not so easy to implement with this approach. And of course, on our domain layer, we frequently or almost always use some libraries, third-party libraries that already implemented in conventional approach, like functional object-oriented approach, and we kind of couple to this implementation, and we have to use this library, so we have no choice where to put this flow-based programming approach. But on a higher level of abstraction, when we deal with application layer, yeah, I use this standard domain-driven design distinction between the layers. On the application layer, there is a quote from Eric Evans' book. On the application layer, we just coordinate the routines, the functions, the methods that we implemented on domain layer. So our application layer is in most of the programs, in kind of the vast majority of the programs, is really simple. It's just a coordination of already implemented routines. So first call that, then call that. If this result, maybe call that, and finally call that. So this on application layer, like if we use this language approach as Eric Evans introduced in his book, on application layer we kind of tell the story using the words that we defined on domain layer. And this story for our application is quite simple. Do that, and then do that. So yeah, and actually if we use this flow-based programming approach, the topology of these components is kind of explicitly defines what will happen in our program. And this topology is predefined, so you can see actually on the picture what will happen with your data, how your program works. What are the advantages of this approach? From software design perspective, and I would say that it's even more important than this technical stuff. First of all, it's clarity. It's clarity or simplicity when you have this simple two-dimensional topology of your components that easy to draw, easy to understand. You can actually print your program and put it on the wall and discuss with your colleagues. And the next, and also this very simple step-by-step transformation of data chunks. So you have a predefined data with some structure, and you can follow this data, pass through each component, and kind of control, see how this data gradually transformated from one view to another. And the second, this kind of buzz phrase, design, coding, and runtime uniformity. What does it mean? That when you, in this flow-based programming approach, when you design program, you kind of drawing on sheet of paper or somewhere else, you draw these rectangles. So first I do that, then after then this thing, then maybe conditionally, if something happens, I go to this branch. So you kind of draw these rectangles. When you implement your program in code, you also define this tree in some way. With DSL language, for example, that I introduced for with this ALF library. You also kind of define all these boxes in your code, and when you run your program, you also have the same boxes actually. Under the hood, you have the same processes, independent, that communicates with in this predefined topology. So actually, what you think initially, and the same structure you get in production. So it's really expressive and really easy to understand. From performance point of view, of course, composability. So you have these components. You can define more or less generic components that can be parameterized. So you can reuse components in different pipelines just to parameterize them in a different way. The second, and maybe more important, this high level of observability that I mentioned, that you can actually see program and can actually detect the fact that packets comes into the component and comes out into the component. And you can observe this and react and make a design decision having this information. The third, scalability. Again, these components works in parallel, and you can easily put several components, like copy of components of each components if you want to achieve more performance. So if, for example, you see that in some components there is a bottleneck, packet takes too much time in specific component, you can just put several components in parallel. And when your program works, now it's kind of, this stage becomes 3 times faster. And of course, testability, it's just a black box. So you write test for this component as you do for your functions. Yeah, so you have inputs and outputs, so it's really easy to test it. And also you can write integration tests for the whole pipeline. Yeah, so very easy to test. There are lots of implementation of flow-based programming in many programming languages. One thing that I want to mention that not all of the implementation are implementation of classical flow-based programming. Most of them are so-called flow-based inspired system. The most famous example is NoFlow.js library in JavaScript that also implement this componentary style that you can define components that connect them, but you know that JavaScript concurrency model in JavaScript are not so good. So actually, you kind of mimic flow-based programming in some sense, but when you run your program, these components are not working parallel, actually. So this kind of flow-based inspired system, but not true flow-based programming. But with Elixir, with Erlang, with Beam, you can imagine that this task can be solved easily because we initially have this actor model process is kind of first abstraction in our language. So in Beam, we have this process. Also in OTP, we have GenServer that adds some level of lifecycle control. Yeah, we have this supervisor restarting mechanism and also this unified synchronous or asynchronous API. And in Elixir, we have a really great GenStage library. I'm not sure if guys from Erlang community heard about that, but what this library does is kind of, the GenStage is kind of GenServer on steroids, I would say, and it does this subscription mechanism to the GenServer, so you can put several GenServers and set them and define this topology, which GenServer will be subscribed to which. So you can define this topology and use as a programming as engineer, you don't care for whom to send messages. You already have this predefined topology. And also, GenStage library adds this back pressure mechanism. So when you put several GenStages into the row, they not actually push data from the left to right, from producer to consumer. But consumer asks data from previous stage asks from previous stage, and only after that, producer push data. So first, GenStage does some work, then inform previous stage that, yeah, I'm ready, give me more packets, and then he can receive this load. So there is no overwhelming in such a system. Okay, and actually in Elixir Erlang, this is a functional programming language, so we kind of mentally ready to do flow-based programming because it's not so different from functional programming. So we used to use this pipe operator or a with statement when we just pass data through set of function. So actually what flow-based programming does is just puts these functions into separate process to do stuff in parallel. So meet ALF finally. Okay, so what is ALF? ALF actually is this very simple library, not so much code there. And as I mentioned, it builds on top of GenStage library, so it's the only dependency. And ALF implements DSL for easily building these pipelines with some predefined components. The second, of course, the API for running all these processes, for starting this pipeline, and for streaming data to this pipeline and get results from this pipeline. And the third very important feature for this high level of observability is telemetry API for monitoring pipelines. So actually, when you enable telemetry for your pipeline, you can react on events when package comes into the component and comes out from the component. And also, if error happens, you can also get a telemetry event about that. And let's check quickly simple examples how you can use this library. So everything is simple. First, you define, you use ALF DSL, and you define the list of components that will be present in your pipeline. And in this simple example, these components are just function names are passed to this stage macros, and functions are defined here below, and they're extremely easy. If you have like more complex functionality, it's also possible to define stage as a module and pass a module as an argument to this macro, and then call function with RET2 will be called on this stage. So as in Plug library, we kind of get used to this approach. So you define this pipeline, and then you just start this pipeline, and under the hood, a magic happens. Each of your function is put to the separate process. Also, producer is added at the beginning and consumer at the end. All these processes are put to the supervisor. I use dynamic supervisor, another great feature of Elixir. So this pipeline is built dynamically during runtime. And also there is a separate pipeline manager. So each pipeline has manager process that's responsible for starting, stopping, and streaming data and getting results from the pipeline. And in order to do something, you have to stream data to pipeline. So the main interface of ALF is streaming interface. So you can put enumerable or stream into pipeline, and as a result of this stream to function, you also get a stream of data. Very good Elixir abstraction, like lazy stream. So until you need results, the stream is not running. So you can actually pass stream to one pipeline, then to another pipeline, and finally call this enum to list, and all these streams will be finally run. So in this simple example, we use one stream. And there is another example. You can put actually many streams into your pipeline, and pipe manager or pipeline kind of handle each stream separately. So you can in parallel run several streams of data into your pipeline, and they will be processed kind of in parallel. let's quickly check what components are available. First, I have to say that these components, this set of components, have nothing common with the components that John Paul Morrison presented in his idea. The idea of John Paul Morrison is more low-level, and components there are more like we used to see in electronic devices or something, when you have like 2 inputs, 1 output, like very electronic-like components. I just kind of get this idea of doing things in parallel, and then kind of was thinking, okay, what I need to design a simple application layer. Yeah, so basically, I need the main component that's called stage, where you put this, your actually logic. Additionally, producer-consumers, as I mentioned, they're kind of implicit components. You do not define them explicitly. The second component that one may need is a switch. Yeah. Also, you kind of, even on a high level of logic, you have to have some level of conditional branching. Yeah. If something happens, let's go this way. If not, let's go this way. Another component, clone. It allows you to do some background work. Yeah, when you have a main track, and in parallel you want to do, I don't know, maybe some logging or some background processing. Also, 2 components, goTo and goToPoint. Why I introduced these components? Because with GenStage library, you can build only tree-like structure of your components. But in general, in flow-based programming, your application graph is a graph in a mathematical sense. It's a network that can have cycles or whatever. So it's kind of graph in mathematical sense. So in order to express any graph, I introduced this goTo. So it's kind of tree plus goTo equals graph in some sense. The next component, that-end, just for example, you can use this with clone. So if you do some parallel background processing and you don't need actually the result of this data chunk of this event, you can just put that-end and forget about this event. 2 more implicit, again, plug-in and plug components. This component are used when you reuse one pipeline in another pipeline. So you can define pipelines that do some more low-level stuff, let's say, and then you insert the, components from this pipeline into another pipeline. And when you insert this pipeline, you have to, in some way, transform data from one prepared data for the inner pipeline and then prepare data for the outer pipeline when they pass through this combination. So this plug-in and plug just to kind of adapters to transforms your data before they comes into the inner pipeline and or comes out. And the last 2 component, composer, decomposer, composer, I mentioned them with this Telegram problem. So actually, the composer allows you to create many events based on one event, and the composer do the opposite. It can kind of collect several events and then finally produce one event. Also quite important feature. Okay, so let's see examples, just to see how expressible this can be. I prepared an online TicTacToe game. You can find the code here. It actually works. Maybe front end it's a bit ugly, but actually you can play with your colleagues or friends online. And here you can see actually the whole program, almost whole program. I cut a couple of pipelines that are not very important, just to fit this map on the screen. So actually you can see the whole program here. The text is really small, no worries. It's just for example that you can actually print your program. There are several pipelines. The top one is user enters pipeline. This code works when client first enters the game. And here we just, in this switch component, we check if token present from the client, so if it's existing users or not. If it's existing users, we find these users and we try to find game. If we find the active game for this user, we go directly to the end of pipeline. If there is no game, we kind of check in if there is waiting game for this user. If there is, we assign user, activate game, and prepare data as an output. So I kind of explained in 1 minute what these pipes do. Another pipeline, game info. Clients periodically call the backend just to check the game status, who should move now. The third one is actually movement, when user send move command to the pipeline, and again, event passes through some checkings. And then you see here game move pipeline. It's here, kind of inserted into this one. Get some checks after the move, and request goes back, and the event goes back to the client. And let's see how it looks in the code. Again, this user enters pipeline. So you see that in your code, you actually what you draw when you design the program, the same you kind of specify in your code. So you can see stage here, validate input, then switch token present, checks if token present. If yes, there are this set of stages. If no, there is this set of stages. Then find free game. Then again, one more switch here, defined here, and then go to point, and the final stage prepare game data. So you can expressively define kind of what you see than what you get in your actually program. Another thing that I want to show to you to emphasize this great level of observability is kind of related project. It's on early stage. The UI is quite messy, but ready for demonstration. ALF Monitor, just to see how easily we can observe the program that written with such approach, how we can get the data about the program, and how can we illustrate it, how we can draw it. So what ALF Monitor does? ALF Monitor is a separate application. Actually, it even doesn't have an ALF as a dependency. It has some knowledge about ALF interface, but doesn't have a dependency. So this ALF Monitor can connect to your working application in runtime. Actually, it can connect remotely to the application that on the remote server. It gets data about running pipelines from the program, and it also subscribes to the telemetry event from the remote server. And then you kind of open your browser, and you can see the application structure, like this map that I showed before. You can see code of each component. You can see state of each component, some internal information, and you can also see some statistic information about component, for how long each component process data, what is the average throughput of components, etc. And also you can trace individual IPs using this tool. And here's a video. I recorded the video. So you see, this is this TicTacToe game. So you can see this pipeline. If you click on a producer, you can see the whole code, actually, of your pipeline. Then let's wait a bit. I'll click to some component. Yeah, find game component. Again, you can see the code of the component. You can see some statistic, throughput, processed IPs, etc. And then I clicked on IPs, and you can see like IPs, like what was the event on the when it comes to the component, and what was the event when it comes out from the component. And also, if you click on a specific event, you can trace this event through the whole pipeline. Actually, what were the transformation of this packet when it passed through each component in the pipeline. Very great tool, very great level of observability in such an approach. And another thing that I want to show you is auto-scaling feature. It's still experimental. I'm not really sure how to kind of correctly, not correctly, how to use it, and you should be use it, but it's possible. So how it works currently? Initially, I should have mentioned that initially you can specify how many copies of each component you will have. So if you, from the very beginning, know that some components will connect to third-party IPs, and you kind of understand that this component might be slow, you can put initially like 5 or 10 copies of these components. But also, it's possible to scale these components dynamically, because we have this telemetry, we have all the data about where packages comes in and comes out. We can calculate this time difference. So auto-scaling feature works really simple. There is a separate process that kind of track all the statistic information. And if producer of the pipeline is overwhelmed by data now, so if it's kind of gets lots of data, it decides to scale up a component. And first, this autoscaler kind of choose the component with the lowest throughput and adds component dynamically, add one copy to this component dynamically. And again, if the load goes down and producer is free, this autoscaler makes a decision to turn off one of the copy of specific component. And again, a quick demonstration. So yeah, it's a really simple pipeline. There are some process sleep added to this add one and multiply two component. Initially, there is only one copy of each component. And now you see it start blinking. The load comes in. And you can see that now we have 2 components of add 1 and 4 components of multiply 2. And after some time, the load becomes less. Yeah, and after, and see that now it's 2, 4, 1, 4, and it will go down. So yeah, really it's kind of experimental feature, but again, you can it's kind of very interesting from philosophical point of view that you can kind of dynamically scale on component level. So you can kind of scale each particular routine in your program in that way. Okay, and actually the last slide. I started from this. From the slide with Donald Knutam about expressibility of software. And I want to mention this idea of ubiquitous language that you know from DDD book, that we, as an engineers, we kind of understand a bit the business side, and also product people understand a bit in our stuff. And if we consider our software as a, let's say, the gradual translation from machine language to the business language, that means that somewhere we have to kind of meet each other. So product guys understand our stuff and try to translate business requirements to more technical requirements, and we are trying to translate these technical requirements into machine language, actually. And actually, this application layer, can be a point when we kind of meet, the point where we have the same language. And especially with this flow-based programming approach, when you define your components, you have these components have names. They explicit names that meaningful names, let's say, and also your data, your business events are also meaningful. You have event, as in this example with TicTacToe game, you have event user enters. You have meaningful fields in these events, user token, username, etc. And this meaningful event pass through these named components, so you kind of tell a story for your product manager using these names that you introduce in your program. And this application layer becomes kind of your meeting point when you actually have the ubiquitous language here, the universal language that you can speak to your product manager, and product manager can speak to you. And you can actually sit together, open this application map, and make a design decision. What can you change in your program, and how can you change your program in order to achieve implement new feature or fix some issue. That's actually it from my side. Thank you.
All right, do we have questions here in the room? No? Those online can check on the Huva app again, make the questions, and then if they...
So what kind of workloads and what kind of work would you ideally use this type of structure for? I imagine sort of a tic-tac-toe game is not perhaps the most challenging, and you don't need the parallelism and all of that. What would you ideally use this for, and what do you think it's less appropriate for in structuring, I guess?
Okay, good question. Actually, I would use this approach for any software in the terms that if you have in your software explicit application layer, I can imagine that most of the software have not such an explicit application layer, but in good software, we always try to have this explicit application layer. We first define domain models, blah, 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 and then for each feature, let's say user flow or use case, we use different abstractions. Yeah, let's say use case. We implement use case module when we have this high-level function. First do that, and then do that. If you have this explicit application layer, you're ready to use this approach. Kind of in terms of performance, you don't really lose anything because this GenStage library is very performant, so there is no kind of performance issues. There are, of course, but they are kind of minimal. Yeah, so you are ready to use it right now, and you kind of achieve this level of parallelism from the very beginning. You can, after that, when you put all these functions into the processes, you can scale your application infinitely. So yeah, the answer is for every applications that have explicit application layer.
More questions? Oh, one here.
Hi, thank you for the presentation. I'm currently writing data pipelines using the Flow library. So I think that the two projects have many pieces that go in common, and I was wondering why you choose to depart from that instead of extending Flow, for example, with your ideas.
Yeah, good question. I would say that even a better analogy will be Broadway library. You know, Broadway library that we use in Elixir for data processing. Actually, that connects. It can connect to Kafka or whatever source of data and just work as a data pipeline. But these, either Flow or this Broadway library, are designed for processing data. The idea with ALF and with flow-based programming to design your program, your application layer. So consider data, not just zeros, ones, but consider your data as a business event that you have meaningful business event with set of fields, and this business event goes through components and you do some meaningful things. So it's more like designing applications, but not for processing data. That's kind of the main reason. But under the hood, of course, it's almost the same. Broadway library also use GenStages to build these subscribed processes to process data. But philosophically, it's different.
Thanks for the presentation. You showed that we can visualize the application map from the code which is already written. I'm wondering if there is a way to do it other way around. So first you design it, maybe visually somehow, and then it actually creates a template or something like this. I'm just thinking about the real example where you sit maybe with a product person and you kind of predefine certain things more high level, and then you actually code.
Yeah, I was thinking about that, but actually now it's not possible, and I think that maybe it's even, you don't really need this, because after you draw these rectangles, implementing, defining this simple set of components is kind of 5 minutes work. So you don't really, maybe with this live book approach, when you can actually code inside the live book. So maybe it will be a great feature if you can place component and write a code of these components, and it will be compiled automatically. That maybe makes sense. But again, it's more like tool for engineers, so for programmers themselves.
All right, do we have more? One? Oh, one there.
Hello, thanks for the talk. So for testing, do you test each layer of your, each component of your application in isolation? And does the library provide some tools and some help to do that?
Yeah, there are primitives. I don't remember right now what I use for, but it's really really easy to run the component and put the producer and consumers. But actually, when you write a test, you can like component actually is a function or module. So if you write unit tests, you don't need actually create this pipeline. For a specific component, you just test it as a usual function or module. But when you write integration test, when you want to put components together, yeah, but it's again, it's really easy. You see that interface of running pipeline is kind of, here it is. So you don't need anything additional. You just define your pipeline, then in your test you run it and pass event to there and check the output. So no extra primitives needed, I would say.
All right, more questions? There's no questions, sorry. There's no questions on the Hoover app, so thank you.
Thank you.